Good afternoon. I'm Jacqueline Brown from Pacific Wave, and I'm also working with LaundryNet. Thank you for coming. Yes. Oh, the microphone. I forget I'm supposed to be like a rock star. Thank you very much. Mick Jagger, sorry. Britney Spears, sorry. I can do Frank Sinatra, but that's about the size of it. Thank you for coming after lunch. It's always difficult not to fall asleep, but I think we have really interesting presentations that will keep you interested. We are going over multiple countries, as is often the case in Terena conferences, but we're also going over 2 continents. We are doing Australia as well as Europe. Our first speaker is somebody who is well known in the Terena and European scene, and it is Alex Reed, who was an IT director at Oxford and is also again well known in the Terena arena, and he's now an advisor to AARNet. Alex.
Thank you, Jacqueline, for your welcome and introduction. Now, how do I get this thing going? Somewhere here, I believe there is a presentation. Here we are. Welcome from down under. G'day. I have to. I won't start with an apology because you're never supposed to start a presentation with an apology. But I have got 2 explanations. The first explanation is, and they may affect your expectations of this presentation. The first is that Chris Hancock, who was due to have co-presented with me, was unable to make it from Australia, so you're left just with me. So although you have his picture there, I'm afraid that's as much as you're going to get of Chris Hancock today. Perhaps next year in Vilnius, he promises that he will try to make Terena. The second explanation is that I'm not a technical, I'm not a techie, and so I'm going to be talking more about the path to virtualization of networks in Australia rather than the technical detail of that virtualization, although I will be touching on that, and I can give you some the contact of a person who can fill you in all the detail if you need it. So I'm going to talk firstly, because we're talking about the path, I'm going to talk about AARNet and its network. I'm going to talk a little bit also about Australia's national broadband network proposals, which have been announced just in April and are quite significant in terms of how Australia is going to get networked. Talk a little bit then about AARNet network services and how they meld with that broadband network, and a little bit then about virtualization network services. I should point out that there's really very little that is new technically here. You all know about layer 3 virtual networks and layer 2 virtual Ethernets and layer 1 optical circuits and dynamic allocation. So there's not a lot of technical novelty in what we're doing. Well, firstly, a bit about AARNet. AARNet is the NREN for Australia. It's a non-profit organisation. It's owned by its members. Its members comprise the 38 of the 39 universities in Australia, plus the CSIRO, which is the major government research organisation in Australia. It has an annual budget of around 46 million Australian dollars per annum. Its funding all comes from subscription and traffic charges. We get almost nothing from the government, or occasionally they will give us a grant for some special purpose. We have 41 people. That's head count, so this is a head. I only work part-time, but I'm counted as one in this head count. And we're scattered right around Australia. It's in 6 different cities, 6 of the main cities in Australia. And so we actually drink our own Kool-Aid. You know, we actually operate as a networked organization using network services in order to operate. We are a licensed telecommunications carrier in Australia, number 61, and so we're entitled to all of the protections of the Telecommunications Act and all the rights and privileges and responsibilities that pertain thereto. We have 24 points of presence. Most of them are in Australia, in the main cities, but some of them are scattered around the world, including one in Singapore and 2 or 3 in the US. We did have one in Frankfurt until recently, though that's been recently decommissioned. We're very keen on peering, and we have something like 280 peers at 14 different places around the world. That is 526 adjacencies. And that, just to put that in context, that compares with Internet 2, which has 139 adjacencies. So we are in fact the most heavily peered network in Australia of all of the network carriers in Australia. And I think 23rd in the world, something like that. In terms of the size of the network, and this is, Trina has a compendium which calculates the size, and the figures actually for Australia omitted some of our international links, but if you include them, it comes to this large number, 410,000, which in fact is more than any of the other entries in that compendium. We pride ourselves on having a very highly reliable network. Our uptime in 2008 on the backbone was 100%. As it happens, this year, 2009, is the 20th anniversary of AARNet, and so we'll all sing happy birthday to AARNet later in the year, September timeframe, I think. Just to, again, put a little bit of context around Australia and the magnitude of our network and of the problems that, the difficulties that we therefore face. Here's a map of Europe. You'll see that there's an area there of 9.9 million square kilometres with a population of about 730 million. On the same scale, there's Australia. It has an area of just over 7.5 million. In other words, not far off that of the whole of Europe, a little bit less than the USA that you saw this morning, but a population only of 20 million. And the 20 million is scattered around those fringe cities. Alice Springs has a population of about 10,000, so in a sense you can ignore that. But the main cities with a million or more are scattered around the fringe of Australia. So we have a domestic network that comprises fibre optics running from Brisbane. I'll see if I can get this mouse working. That's not right. I don't understand Spanish, so I can't make it work. So I'll just do this. Anyway, from Brisbane here through Sydney, Canberra, Melbourne, and Adelaide, we have our own fibres on, I think, 15, 20-year IOUs, and we're running them at 10 gigabits and on diverse paths to provide resilience and also to bring in, as we see later, a number of the regional sites that we want to incorporate. At the moment, we do still have, we also have 10 gigabits across to Perth, across here, but that's we only have one circuit lit at the moment, though we do have a second fibre. We haven't yet been able to afford to light that fibre, and you'll see the relevance of that in a little later on. And to Alice Springs and to Darwin, we only have fairly low speed connections, and also to Hobart, although we are hoping to get fibre connections to Hobart before too long. And then we have also 2.5 gigabit links up to Cairns. In terms of our international network, we have links into Singapore and also across the Pacific that take in Suva and Honolulu, and then to Seattle, Palo Alto, and Los Angeles. This is our domestic optical network in more detail, and you'll see that it takes in a number of these inland locations, which are particularly relevant because places like Parkes, Narrabri, we have significant radio telescopes located there, and these are now connected at between 1 and 10 gigabits per second links back to Sydney and thence across the world. And our international optical connections are shown here. We have, again, two 10 gigabit connections. The northern link which is mostly for IP traffic, although we can in fact route that as optical circuits as well, and the southern path, which is dedicated to optical circuits. We can have, I think, 9 1 gigabit light paths, of which one, for instance, is dedicated to EVLBI, and others are available on a demand basis for particular experiments. And then I should say that ARNET carries all kinds of traffic, both commodity traffic and research and education traffic, and this is relevant also in how we've had to divide up the network. So these two links can only carry research and education traffic. The way that we've negotiated that with the provider, Southern Cross Cable Networks, they can only carry research and education traffic, whereas the rest of the traffic, commodity internet traffic, has to go on these other routes, which operate at 2.5 gigabits. And of course, we slot into the worldwide optical connections, the glyph map. And it shows our northern leg, although we don't often use that for optical circuits because we can, in fact, allocate optical paths on that circuit as well, if we need to. A little bit about the National Broadband Network, which the government has announced. It actually initiated this some time ago and it had a tender process, called for tenders from all of the major suppliers in Australia, including Telstra, which is like the PTT, or was the PTT, but gradually the government has sold that off. So it's now a private company. And it was offering $4.7 billion to try and wire up Australia for broadband for the community. However, that was then cancelled earlier this year without awarding contract to anybody. And instead, the government announced that it's going to commit to a new system which would cost $43 billion. They were going to initially eject this $4.7 billion which they had allocated to that tender process. It would be owned by the government, so in a sense turning back the clock on the government-owned PTT, but they're hoping for a considerable amount of private input, perhaps private capital, certainly private. They want anybody who's got fibres to contribute them to the party, so to speak. So the target date for this new project is 2017. We don't have a lot of detail yet about what it's actually going to do, how it's going to be managed, but we do know that they want to put fibre to the home or premises. They're claiming that they will provide 100 megabits per second to 90% of the population of Australia. And as you know, as you're seeing from that map, most of Australia's population is gathered in those fringe cities. In fact, Australia is about the third or fourth most urbanised nation in the world, despite the vast size of the country. Nobody lives there, and so they all live in these cities. And so, in fact, wiring up that 90% of the population is not too difficult a task, other than the intercity connections, which of course are over long distances. And then it's expected that 12 megabits per second will be made available to the rest of the population that live in the outlying areas, either via wireless or via satellite, and some of them, of course, are extremely remote. A particular initiative which was announced a few weeks later was this, what they call the backhaul black spots initiative, to which they were going to commit. They are committing 250 million Australian dollars. The idea is that Australia has a number of regional centres, some of which are very poorly served in terms of backhaul. That is, the main incumbent, Telstra, is the only one that provides backhaul, and so they just charge what they think is the market will bear, and there's not really much competition. And so they want to see competition develop on these links to regional centres, backhauling to the nearest major city. They're inviting organisations to install, to keep some, and to offer the rest of the fibre to the community. In fact, this is exactly the model that ARNET has been adopting most recently, in that we're looking at installing fibre in a regional location, backhaul to a city, and then, because we don't want to compete with the commercial world, we will then offer the other circuits, the other fibres or circuits on those fibres back to any commercial provider that then will be able to provide that to the rest of the community. So this is, we've in fact been in quite a bit of discussion with the appropriate department, and it looks like that they've taken up that idea, which suits us well because there are a number of regional centres that we still want to get to, and if we can get some of this 250 million, then we may be able to connect to those. A particular one of interest to me is Geraldton, which is 350 kilometres north of Perth, which itself is about 300 or 400 kilometres from the site of ASCAP, which is the Australian SKA Pathfinder project, and we hope will be the final location of the square kilometre array. And obviously that needs to be well fibre connected. We are in the process already of putting in fibre from that location back to Geraldton, the town of about 30,000 people. But again, getting it from Geraldton back down to Perth, another 350 kilometres, is proving quite problematical. And so we're hoping that this sort of injection will not only serve our needs, but will also serve the needs of the community of those regions, which is the main goal of the government. So this was announced a matter of 6 or so weeks ago, and they want rapid deployment. They're hoping that some of this fibre will be deployed this year, so it's really quite rapid proposal. ARNET's attitude to the National Broadband Network is one where, of course, we obviously welcome this initiative. You know, if Australia, as is claimed, will then lead the world in terms of connectivity for its citizens via ordinary broadband, well, we want that for our students, we want that for our staff at home and so on. Whether, in fact, it does lead the world, by 2017, things will have moved on a lot. But nonetheless, 100 megabit connections will still be very nice. And as I've indicated, there's a synergy in particular in relation to this Black Spots program, which clearly we've been keen to applaud. We want to collaborate and cooperate with that initiative wherever we can. However, there are some things I think are going to take a long time for the government to move on, but there are some of our projects we need to require action now, so we are hedging our bets on that one. And a certain amount of regulatory reform is vital to make this work. But the final point, of course, is that NRENs are different from standard community networking requirements. As you can see from this table, if you look at 2009, you'll see that a typical home in Australia might have between 1 and 20 megabits per second connection. 20 megabits would be really fortunate. 1 is probably more like the average, certainly in terms of real capacity. Leading edge homes or businesses or government might have between 100 and 200 megabits per second connecting their facility, and even that's probably very optimistic. Whereas research centres, like major university campuses and things like telescopes and so on, we're looking at 1 to 10 gigabits per second. So that's the current situation. And if you look back 8 years, that's been growing at a rate of about 50% per annum. And so these are the figures which roughly equate to what, in fact, was happening in 2001. Projecting forward at the same rate, we'll be looking at homes between 25 and 500 megabits per second. So that's the goal of the National Broadband Network. Perhaps some leading edge homes or businesses will have rather more than that in the gigabits. But by that time, we will be looking at requiring 25 to 250 gigabits per second at least. So that sort of puts into perspective the fact that NRENs are require something like 1,000 times more capacity than typical homes. And that probably will always be the case. Now, so ARNET has developed its roadmap. It developed the roadmap before it knew about the National Broadband Network, but it matches to the kind of progress that's being made. You'll see that our basic backbone, the DWDM backbone, is currently 8 by 10 gigabits. We're expecting within 1 to 3 years that'll be 8 by 40. We've already deployed one of those 40 gigabit links. And within 3 to 5 years, we're looking at 8 by 100 gigabits in order to meet that kind of demand that we see happening exponentially. So our IP backbone currently is 10 gig, as I mentioned. That'll go to 40 gig shortly, and then 100 gig within 3 to 5 years. And then the various services that we layer upon that will also reflect not just the increase in speed, but also increase in capability. Right, I'll need to speed up a bit. These are some of the network services that ARNet provides. Obviously, we have this IP network offering 1 and 10 gig connections. We do offer dark fiber where we have dark fiber. We don't actually have a lot of dark fiber at this point in time, but there are some places where we've actually dug trenches and laid fiber ourselves, where there's not been any alternative. We obviously offer wavelengths, optical circuits with a thing called EN4R, which is experimental network for researchers. We're planning to make that into a dynamic capability using dynamic circuit provisioning, and we've joined up with the Fenrir team to try and move that ahead, and we're hoping that before the end of the year that we'll have an initial deployment of DCN. Where we don't, so the whole of Australia is not covered by our optical backbone, as you've noticed. So for instance, to Perth, although we have 10 gigabit link, that's used for IP traffic and not conventional traffic, and similarly for Hobart and Darwin. But we do want to deploy the same kind of services to those locations. And so we're using, currently deploying VPLS over MPLS and VLANs to achieve the same kind of capability. So you just plug in the circuit as if you were plugging into optical circuits. Then we want to move that into a dynamic form, and that'll be a little further off, although we're working on the design of that at the moment, so that people like the astronomers can fire up their network as they need it. It also, the design will also allow us to do traffic routing. So you recall I said that across the Pacific there are certain circuits which we can only use for research and education traffic, and so we have to route. We have to split up the traffic when it reaches Sydney and say that some of that can go on that route and the rest goes on another route. And the same kind of capability allows us then to provision rate-limited IP connections where, because we charge for network services, some universities want to limit their exposure to cost, and so they're looking at rate limiting some of their connections. I've already mentioned that we have virtualization that can occur at all those 3 levels, layer 1, 2, and 3. The technology on which we're deploying all of this allows us to do various things, and in particular, the NCN is what we're calling the capability of providing that kind of simulated optical circuit right across our network, which I'll say a little bit more about in a moment. And I should just go back. There's one thing I should mention. We call on-net the research and education traffic and off-net the commodity traffic. And so using layer 3 VPNs, we can distinguish between these two and route them over different circuits. So the National Collaboration Network was an initiative to try and set up a transparent community of researchers who are collaborating together in a way that would avoid all of the problems associated with going through the normal campus networks. So in particular firewalls, for example. It hasn't actually worked out hugely that way because most of the devices which you would want to connect to this sort of collaborative network, and you see this is a kind of layout of the sort of thing we want. We have a member here in Adelaide connecting to another member here in Canberra and another member here in Sydney over this virtual over these virtual paths. So it's a virtual private network to suit those 3 members, and of course the same member may be part of another virtual party as well. It hasn't actually worked out too well because most of the devices which you would want to connect are also connected to the campus LANs, and so if they're connected directly into this network, this will provide a backdoor for avoiding the campus firewall. So we're still to resolve that, and indeed we're still to find out suitable applications for this technology. So if you've got any ideas, we're very interested to hear. Just very quickly then, some of the applications. I've mentioned IP traffic on and off net, rate limiting traffic types, routing different types of traffic, VPNs, virtual organizations, high definition video conferencing such as medical applications, privacy preserving, eVLBI over optical circuits and over a mixture of optical and IP circuits, dynamic eVLBI, and here are some examples of the things that we've done to date where we've actually used this approach to try and be involved in these international research projects. So here's one that took place in August 2007, connecting up our telescopes back to Jive. Medical video conferencing, although it says here Professor Shimazone-san, it's not him actually, it's a Korean colleague of his, but you probably, those who like gory things have probably watched him demonstrating this outside. And there is a tiny bit of gore here, but you have to look very closely to see it. OptiPortals, we've also been, we have our own OptiPortal, and there's a number of people, number of universities in Australia now with them, and we've been trying to, this is ours here, we've been connecting them up together using a variety of different circuits. So here's one we did in January last year, where we connected up some of these OptiPortals over a 1 gig dedicated path with a backlink over our IP circuits. So that's the sort of capability that we want to try and achieve using this technology, and that's the end of my talk. So if you have any questions for me, I'll be happy to try and field them. However, I should refer you to a colleague of mine, Ivan Phillips, which is ivan.phillips@arnet.edu.au. If you want to know any of the technical details, I can't help you with that, I'm afraid.
Thank you very much, Ivan.
Okay.
Does anyone have any question for Alex? If not, I have an announcement. I waited to make this announcement until there were more people in the room. Somebody, I'm sure just by accident, swapped his or her conference bag with somebody else's. That particular bag, which was swapped, contained a very nice laptop, so the owner would very much like the bag with the laptop, please. So if you have by mistake picked up that bag, please return it to the Secretariat, or if you hear of somebody who knows that they have picked up the wrong bag, please refer them to the Secretariat. Thank you. Our next speaker is from Poznan. He has presented a number of times at Terena. His name is Bartek Belter, and he is from the Poznan Supercomputing and Networking Center.
Okay. Thank you, Jacqueline. I'm Bartek Belter from Poznan Supercomputing and Networking Center. No, thank you. Last year, I had the chance to provide you some technical background about the grid-enabled network control plane. This year, I will focus on the results of experiments and integration activities we did in Phosphorus in the integration between applications, grid middleware, and G2 MPLS. So I will start my presentation with a short, very brief introduction to GMPLS and G2 MPLS protocol stacks. Then I will focus on the Phosphorus testbed for a moment, and finally I will show you the results of the validation between the applications, grid middleware, and G2 MPLS protocol stack. I would like to highlight the TNC2009 demonstrations, which you can see on the booth, Phosphorus booth. This is the booth number 10 in the lobby. So I will start my presentation from GMPLS. So this is our base for further work. So we have two phases in the Phosphorus project. In the first phase, we were focused on the native GMPLS. So we developed it and designed it based on the Quagga. And we finalized the work in the first year of the project, and we released the software under the GPL version 2 license. We released the prototypes in a form of Xen virtual machines, so anyone can download them, plug to the Xen virtual machine, configure it, and play in your testbed. And the images are available on the Phosphorus website. In our GMPLS protocol stack, we identified 4 different kinds of the controllers, and the type of the controller depends on the location of the controller in the network. So we have a GMPLS border controller for to establish the adjacency with the neighboring GMPLS-like domains. We have the edge controller to attach the clients of the network. We have also the core controller, which runs on all the other devices in the network. And finally, we have the UNI client controller, which runs directly on the machine attached to the network. So what is the position of the Phosphorus protocol stack with regards to the standards? So basically, we implement, in our Phosphorus GMPLS, we implement the ASON architecture. We also follow the recommendations given by OIF. So we are compatible with the UNI and ENNI interfaces. And finally, we follow the recommendations given by CCAMP working group at IATF with regards to the protocol controllers and some architectural aspects. So as I said, the first step was to develop the native GMPLS protocol stack. From this, we'll move to the G2 MPLS. So what is G2 MPLS? This is an enhanced network control plane. So it forms the uniform interface for grid applications. This allows a single-step provisioning of both grid and network resources. So we adopted the well-known procedures from the native GMPLS to G2 MPLS. The G2 MPLS is made of this set of extensions applied to native GMPLS. So we took into consideration the GSDL scheme developed in OGF, and we mapped it into the GMPLS signaling protocols. We also took the glue schema, which is the language for the descriptions of the grid resources in the grid environment. So we map these descriptions into the GMPLS routing messages. So let's have a look at the Phosphorus testbed. In my slides, I will focus on the part of the testbed. This part was involved in the validation of the protocol stack. So the first one, it's a transport plane. So the Phosphorus project addresses mainly the optical issues in the networking. So in the first step, we developed interfaces to the lambda switch capable devices and fiber switch capable devices. And the representative of the first group is ADVA FSP 3000, and the representative of the second group is Caliant. The interesting thing with Caliant is that we were able to partition it in that way that we achieved a number of virtualized Caliant switches, and each of them may be run as independent device in the network. Then we realized that it would be useful for us to extend the functionality of the control plane for Ethernet. So we addressed also the layer 2 as well. So first we started with Foundry XMR and Melix devices because we have such devices deployed in the production environment in Pioneer network in Poland. So we implemented interfaces to these devices. Then the users have asked us if we can provide the functionality for access networks as well, because the first 3 devices, optical plus Foundry, with these devices you can build a quite complicated core network. But the expectations were to get the control plane to control the access devices as well. That's why we decided to go in the direction of low-cost Ethernet switches. So at the end of the project, I would say a few months ago, we developed the interfaces to Allied Telesis switches. So we have a representative of fast Ethernet switch and the second one gigabit Ethernet switch. So with these switches, you can easily download the binaries of the Phosphorus protocol stack, deploy it in your testbed, and play. And this picture presents the overall architecture of the Phosphorus testbed in PSNC. So we can see on the top the Ethernet domain with 3 core devices and 2 access devices. To these access devices we have grid sites attached. We have also the LSC domain on the left with ADVA devices and FSC domain on the right with 4 virtual machines, 4 virtual client switches. The second testbed used for the validation of the stack is in University of Essex. They have one physical client device. We are able to partition it in that way that we have 4 independent devices, and each of them is controlled by different controller. We implement the connectivity between the PSNC and University of Essex testbeds via JANT network. So now let's have a look at the control plane. As I mentioned earlier, in the control plane, we implement a number of node controllers, and in G-square MPLS, it's exactly the same. So each controller operates exclusively on the transport plane devices, either a real one or the virtual one. And we interface with the devices with either with TL1 or command line interface or SNMP. I must mention also about the signaling control network, and this network is used to exchange messages between the components of the control plane. We use out-of-band connectivity, and for this purpose we use IP tunneling. Now, when you have your network, when you have your testbed, you have to run a control plane on top of it, and the mapping of the actual physical topology into the configuration file is quite a complicated process. So it is good to have a picture of your testbed and picture from the transport plane, but also it is good to have a control plane picture which explains all the details. So this picture presents the part of the testbed. It's quite complicated. I'm pretty sure you cannot read this, but you see the main boxes here. So on the left side, you see the client controller, which is run on a grid side, and you can see 4 controllers running directly on the physical devices. Please note the red box, which implements the multi-domain routing controller. And now I have discussed the transport plane layer, control plane layer, and now it's time for middleware and applications. So we decided to go in the direction of Unicore 6. I'm not an expert on Unicore and in grid middleware in particular, but I know that Unicore is a management system for management of the computing resources. So the development has been started in Germany 10 years ago, I guess, and we have the core developers, active developers in the consortium, in the Phosphorus consortium from Jülich. On the top of the grid middleware, we have deployed a number of scientific applications, ranging from the simulation environments for atmospheric processes, through the some health applications, through the visualization applications, to the distributed data storage systems. In my presentation, I will focus only on CodeAvis because we decided to use it to validate our control plane. So the CodeAvis is a simulation. With CodeAvis, you can simulate the physical and chemical processes in atmosphere, and this helps you to understand how the human activities affect the climate. This application is a visual application, so and it allows collaborative work. So many clients can connect to the data server and work on the same set of data. In this way, they can analyze the processes and analyze the factors which affect the climate changes. We have deployed the application in a number of nodes in Phosphorus project, in the Phosphorus testbed, and also we have deployed the application in the testbed in the booth, the Phosphorus booth. The application has strong requirements on bandwidth. It requires 700 megabits per second and 10 millisecond latency at the client side. And the data server side, it requires n times 700 megabits per second, where n is a number of attached clients. So, this is the old presentation. Let me, if I can skip this, I know where the presentation is. Someone did not exchange it. I'm very sorry for this. They have downloaded it, but not changed. So now I will show you the results of the experiments with the G2 protocols, MPLS protocol stack in the testbed. And I will focus on the TNC demonstrations. So there are two demonstrations available at the Phosphorus booth. The first one shows the results of the integration of Codavis, Unicore 6, and G2 MPLS. The second one shows the direct interaction between the application and control plane without any grid middleware. So the main building blocks of the first demonstration are the Codavis client and two Codavis servers. These Codavis applications talk directly to Unicore 6. And Unicore 6 asks the G2 MPLS control plane to allocate the resources. This is how the testbed looks like. So we have 4 virtual Ethernet switches. I say virtual because we were able to virtualize the second switch to 3 virtual nodes. So in summary, we have 4 of them. And we have 2 Codavis servers attached to the network and 1 Codavis client. This slide presents the design of the control plane with all the details. So these details are have been mapped to the configuration files. And for the demonstration purposes, we have identified 3 scenarios. The first one, reduced overlay mode. Second one, pure overlay mode. And third one, integrated mode. The first reduced overlay mode means that the grid layer has no information about the routing at the network side. So the scheduler just asks for a path from the client application to directly to the server. So it knows the location of the server. I'll explain this on the picture. So you can see the brain at the Unicore layer. So it sent a request for a network quality of service from the client to server. And then MSS is a meta scheduler, part of the grid middleware, sends a reservation request to the network. And then the network reserves the path, creates all the responses, and then scheduler responses with the network SLA to the Unicore client. So the Unicore client can monitor this SLA, and when the path is available, he will start this Codavis session, he will load the visualization, and finally, the visualization client will connect to the data server. On this slide, the important thing is a brain, which is at the Unicore level. The second scenario presents the overlay mode. In this scenario, grid layer has both grid and network routing information. So the grid scheduler now is responsible for the initiation and coordination of the call. I will explain it on the picture. So now Unicore client sends a request for a network request from the client to any server. So it doesn't care where the location of the server is. And now the scheduler has to know the routing information. So MSS will ask the network, please provide the information about grid and network topology. So the network will respond with this information, and the MSS will select the data server to connect. So then everything goes as previously. So MSS will ask the network to set up a path, and finally MSS will create the network SLA. So the Unicore client can monitor this SLA and creates new session when the path is available, loads the visualization client, and finally connect to the server. So now the logic, the grid logic is moved to the below the closer to the network, and the scheduler decides about everything. And now it's a final scenario where all the functionalities are moved to the network layer. So now the network decides about everything, because only the network has the whole view on the resources available. Let me explain this with the picture. So Unicore client again sends a request to connect the client to any server available in the network. And MSS right now forwards this request to the network. And the network itself will select a server and reserve a path based on the routing information available in the network. So when the network is set up, it responds to the MSS, and it will respond with the server address because it has to notify the MSS, the grid layer, about the exact location of the server to connect. And then the Unicore client again monitors the SLA, creates new session, loads visualization, and connects to the data server. So now the brain, the logic is hidden in the network. And this is the picture, or the topology of this demo. And this demo is available on the Phosphorus booth, so you can see it. The second demo is a simpler one. It's a DDSS backup. It's a simple application written in PSNC just for proving that our concept works. Right now we have no grid middleware layer. We have just only the application, and this application directly talks to the network control plane. In this scenario, we implement the multi-domain and multi-technology testbed. So we have two network domains, one in PSNC and one in University of Essex, and these domains are interconnected with 1 gig link over JAN2. And the application offers a backup functionality to the user. So the user can select a file and ask a network to back up this file somewhere in the network. And the network decides, based on the capabilities of the servers available in the network, where the file will go. This demo is presented remotely. So all the facilities are located in PSNC, and the demo is remotized to the booth. And this demo uses the Anycast feature. So this is the last scenario presented previously. This is an integrated mode. And this is how the testbed looks like. So on the right, we have the University of Essex testbed with DDSS servers connected to the network. In the middle, we have PSNC testbed with DDS client application, which is remotized to the demo booth. Okay, so now I have to thank many people involved in these demonstrations, because thanks to all of them, the demonstrations were possible. So I would like to thank people from Nextworks, from PSNC, and from University of Essex. This is a G-Square MPLS development team. And I would like to also thank to people from Grid middleware and application teams, namely people from Jülich and PSNC again. Thank you very much. Well,
thank you very much. I didn't even have to make any gestures.
yeah.
Thank you. Are you awake? Any questions for Bartek? You're not awake. No question? Thank you very much. Our last speaker is Peter Stefan from the Hungarian National Network, and his specialty is high-performance computing and grid. Peter.
Thank you. What does this mean?
Middle button, please. Cancel is the middle button.
Cancel is always a good selection. And then, presentation, I guess. And this is the right button? Yes, it's okay. Ooh. Okay, thanks for helping me. And thanks for the chair for introducing me. Besides the Hungarian National Research and Education Network, I'm also representing the Nordic Grid Initiative, which is called NOARC. So without abusing your time and your next 20 minutes, I would like to introduce a project which is called NOARC. This is basically a grid middleware development initiative. And I would like to, it's actually a 3-year-old project approaching its end. And it's high time to share the project results with a networking community like you here. So first I would like to give you some background information about the people and the community behind the project. This community is called the NordoGrid collaboration. I guess how many of you have heard about NordoGrid before? Okay, so you know this initiative very well. Then I would like to introduce NOARC, the project itself, its objectives, and emphasizing its distinguishing features. Then I would skip to the available ARC services, if you consider using ARC for your purposes. Then we'll come to technical slides about the middleware, then the current status of development, what has been achieved, what has been done so far, and what is available. Then what should be done in the near future until the end of the project. And finally, to conclude my talk. So NordoGrid is basically a grid research and grid development initiative which originally targeted to integrate Northern European data centers. It's a 8-year-old initiative, and it has 3 basic objectives. First, to develop and coordinate the development of free grid middleware solutions. Secondly, to support data centers in integrating themselves by using grid middleware. And finally, to contribute to grid standardization initiatives. NordoGrid's main product is called Advanced Resource Connector, abbreviated as ARC. And it has been used in production since 2002. By the time I wrote these slides, there were 74 sites connected using this middleware and integrating roughly 38,000 CPUs together into a single large compute facility. Since it has been used on numerous production sites, and since it has been quite widespread, not only in the Nordic countries, but also besides these countries, the collaboration decided to further develop the ARC middleware, and we began a project which has been NOARC. Its official name is Grid-Enabled Know-How Sharing Technology based on ARC services and open standards. It's a research project. Originally, we planned a 3-year project, 3 years project, but we had to extend it due to quality assurance reasons. This is not its original duration. Originally, it should have been terminated by May 2009. It has 7 work packages. Each work package focuses on different aspects, different parts of the project. And currently, there are 9 partners involved in this project. The next slide shows a map about which countries are involved in this initiative. So the pink countries are involved in the NordoGrid collaboration, and the orange countries are involved in the project. The coordinator of this project is the Oslo Universities, of Oslo University, and there are 4 Nordic, we call core universities in the initiative: Lund University, Copenhagen University, and Uppsala University. And besides these core partners, there are NIF, University of Geneva, Josef Schafarik Institute in Košice, University of Lübeck in Germany, and the exploitation efforts are done by Emergence Technology Limited from the UK. There used to be 2 more partners in the project, Science and Computing from Germany, and also some microsystems who stepped out of the project. So what are the objectives of this project? First, to significantly contribute and improve the old ARC software. We usually refer ARC in 2 ways. So ARC is a single product, but there are 2 main, not branches, but main directions. The old direction, what we call ARC Classic or pre-web service ARC, usually refers to the original ARC components, which are not web service based. These components were not developed in the new ARC. And the very first objective is to improve the ARC Classic, both in terms of the number of services. So we plan to introduce new components, and also in quality of the code, in quality of the documentation, and also the quality in terms of standardized interfaces. The second objective is to follow up grid technology take-up. It is highly important to take part in standardization processes. This is a bidirectional process, which means that on one hand, we follow the standardization initiatives, like OGF, like OASIS, like IETF initiatives, and we try to evaluate what kind of standards are important for us and what are less relevant. On the other hand, we also try to contribute to these standardization initiatives, feeding back some implementation-based information to the standardization bodies. And also, it's also paramount importance to promote this piece of software on as many operating environments as possible. So what are the ARC components? Basically, there are 6 components currently, 6 major components. The first one is the hosting environment, which is abbreviated as HED. The D refers to daemon, the operating system daemon. This is a generic container in which we can plug in different services and execute them on a site or on a machine. In brackets, I put the standards which are supported by the component. So the head basically supports TCP standard, HTTP, and XML standards. Execution service is called AREX, which supports BES and JSDL from OGF. The third service is information system, which is a brand new information system. Classic ARC had an ADAP-based information system, which had been quite successful, actually. But in the new ARC, the next generation ARC, we developed a peer-to-peer based grid information system, which we believe that it's more efficient and more scalable than the old solution. The fourth service is the storage system. So we have implemented a full storage subsystem in this initiative. It's important to note that the client side has a client-side library component. So we plan to put all the the most important client-side functionality into a client-side library, which can be used by the client tools, either command line tools or graphical tools. It basically involves an interoperability abstraction layers, which allows us to access different grid middleware, different sites operated by different grid middleware, and also performs job description translation between one job description language to another job description language. So the native language of ARC is XRSL, but we also, by using the ARC library components, we can translate the job description or the translatable part of the job description to JDL and JSDL. The other component of the ARC client-side library is the resource broker, which is the classic client-side resource broker of the ARC. And the sixth component, which is not a separate component, performs the security involving authorization and authentication functionalities. We support XAML, SAML, and X509 standards here. This figure shows how the ARC is built up. On the right-hand side, you can see the server-side components. So this is the hosting environment. I think this doesn't seem to work. Hosting environment, which is the generic container, the daemon process on the site, in which you can plug in the different services, like AREX, like eco service. This is for test purposes. And this is fully web service based. And on the left-hand side, you can see the client-side components. This is the client-side library. And the clients can access the services through the client library, which use adapters. By using these adapters, we can access the new ARC services, and we can also access the classic ARC services, but we can also access external components like G-Lite Scream execution nodes. This figure shows how the head is built up. The head basically is a huge switch and a set of communication elements which can be chained into a communication chain. So we can arbitrarily build up any reasonable communication channel based on, for example, TCP, TLS, HTTP, all together constituting a communication channel. And we can build up several communication channels. And there is a plexer components which can switch communication messages between these communication channels. Besides this switching functionality, the head also provides configuration file analysis related functions, loader, which helps loading and unloading the different components, the information engine, which helps the information system to propagate information, resource and site information. There are also some logging functions and a counter function in the head. So the current achievements of the project. So previously I showed you 6 services. These 6 services are in pre-production phase. They have been extensively tested. And even one service, the job execution service, plus the head, has been put into the latest ARC release, production release. So this statement here is not fully true because one component plus the head is already in production. Due to the interoperability abstraction layer in the ArcLib, we are able to submit jobs to G-Lite Cream 2 nodes, and also to follow the execution of those jobs. ARC tries to comply with OGF, IETF, OASIS standards, and we have also got a standardization roadmap. Every year of the project, we surveyed the available standards and evaluated what can be relevant to the project and what can be less relevant. And we wrote a standardization roadmap on those 3 years evaluations. Currently, Arc is available on most popular Linux platforms, but it's also available on Solaris, on macOS, and also on Microsoft Windows. On Windows, currently the client-side components are available, but we are working on the server-side components as well. The job execution service has a thick, well, not really thick, Globus dependence. So the first problem was porting Globus toolkit or certain parts of Globus toolkit to Windows, but it has been successful. Really good news for the developers that the Arc has a language binding feature, which means that you can develop services in 3 programming languages. Currently, C++, Java, and Python languages are supported. The head also supports IPv6 communication. Individual services may open IPv4 communication, but it's up to the service developer to support IPv6. But the head doesn't exclude using IPv6. Arc also supports dynamic runtime environment, or which is called Job Sandbox, and also supports virtualization. It also supports job persistence, which means checkpointing jobs and restoring jobs at other sites. Arc is currently involved in the Unified Middleware Distribution Initiative along with G-Lite and Unicore. And there is an intensive work in the OGF PGI profile. The latest production release of Arc is 0.6, which was released in May. And there's going to be a technology preview release in the 3rd quarter of this year, which is coded as 0.9. something. This release will involve all the new components, all the new NOARC results. So far, I have talked about what has been achieved. The project has roughly 5 months to run, and there are some work to be done ahead of us. So the very first thing that should be done in the next couple of months is to finalize the project. I put this smiley here because it's not always an easy task. So we need to wrap up what has been achieved, and we need to determine those tasks that are necessary to be done before termination of the project. These tasks are the following. First, we would like to develop native graphical user interfaces for the Arc client-side libraries. We would also like to certify the code, also to release the technology preview release branch. We would like to submit to evaluate the new components in terms of their usability and try to improve in the remaining time. It's important to exploit and disseminate the results. So we would like to talk to those communities who already know what grid is and how, for what can grid be used. And we also try to survey the possibilities of industrial usability, which is referred as exploitation here. It's important to write case studies for numerous scenarios in which Arc can be used in. And we would also like to be getting more and more involved in the unified middleware distribution and also in the PGI work. And last but not least, to document and document and document all of the results of the project. So let me conclude my talk. So ARC is, what I have been talked about, ARC is a grid middleware called ARC, which is a next generation powerful grid middleware that carries both the strength of the classic or pre-no-ARC middleware components while improving those components significantly. I mentioned a couple of distinguishing features of this middleware, like standards compliance, interoperation capability, web service capability. We support multiple platforms, IPv6, and numerous programming languages can be used to develop service components. Currently, there is a pre-certified ARC branch available to try. It can be downloaded from the project website, which are the following: www.noarc.eu and www.nordogrid.org. So I would like to thank for your attention, and if you have any questions, please let me know.
Thank you very much. Thank you. Any questions for Peter? Come on. No questions? Thank you very much. Please join me in thanking our three presenters.